All right, so far we talked about the compression and tension, and now we want to talk about the shear stress. Let me just refresh your memory again. For example, if we have a bar like this, and if there is a force applied to this bar is in tension. All right, and we talked about it before. If we split this bar, the top part of the bar is in compression, and the bottom part of the bar is in tension. Compression and tension. And we talked about compression and tension. How a beam can be in compression, or in tension. For example, if there are two forces applied to this bar from these two sides along with axis, this bar is going to be compressed, right? So this bar is going to be in compression. And if the forces are still applied along with axis, but it's going to elongate the bar, this bar is going to be in tension. We all agreed with that, right? And we all agree this bar is gonna look like this after some time, and this bar is gonna look like this after some time. It's gonna elongate and it's gonna be compressed. All right, now we want to talk about shear stress. We talked about compression stress and tensile stress or tension stress, and now we want to talk about shear stress. What is shear stress? If the force is applied perpendicular to the bar's axis, it's going to be on shear stress. For example, if we have a bar which is stuck to the wall from one side, and if we have force perpendicular to its axis, it's gonna have a shear stress. Or if I just draw it another way, for example, we have two beams. If the force is applied from this way, another force is applied from this way, it's gonna have shear stress, all right? And if the stress is bigger than its strength, what's gonna happen? It's gonna break finally. Or let me just draw you another example. For example, if we have object which looks like this, all right, this is ground and this is ground, all right? If there is a force in this way, because it is in equilibrium and we want to maintain the equilibrium, the object produce the force in this way as well. So this is the shear stress. Or if there was a bolt in this material, for example, we want to stick two beams together using a bolt. For example, we have one plate and we have another plate. If you want to use a bolt, if you want to use a big bolt like this, and stick these two materials to each other, the object is going to develop shear stress because why we are putting this bolt? Because this doesn't break. This doesn't go far away. So it is going to have shear stress. Shear stress is perpendicular to the object's axis, but the compression and tension stress is applied along with the axis. Okay, perpendicular along with the axis, perpendicular along with the axis. And when we want to calculate the shear stress, we use this formula. Tau equals P over A, which tau is the average shear stress. P, as we always had it, is the external applied shear force, and the A is the area over which the stress develops. And if we have A in inches and if we have P in pound, the tau is going to be, of course, in PSI or KSI in the American system. And if we have P, just write it down again. And if we have P in newtons, and if we have A in meters, we're gonna have tau in Pascal, or millimeters we're gonna have it in megapascal. So for shear stress, we're gonna use this formula. All right, example 9.9. The question says the lap joint in this figure consists of two steel plates connected by two a quarter inch diameter bolt. So the diameter of our bolt is 1/4 inch. For a tensile load of P of 18,000 pounds, and P is 18,000 pounds. Compute the average shear stress in the bolt. So we want to know what's tau. So based on our tau equals P over A. So we have tau equals, what's our P is 18,000. And what's the A? A says the diameter of our bolt is 1/4 inch. So if we say the diameter of our bolt is, let me just calculate it. Is 7.5 inches. The radius is gonna be 0.75. So the radius is gonna be 375. 0.375. And the area is gonna be PR2. So the area is gonna be, if we do our calculation, pi R2 is 0.442 inches. So 0.442, and tau is 20,400 psi. All right, example 9.10. What does it say? 3 pieces of wood are glued together to form the assembly shown in this figure. These are 3 pieces of wood. It can be used to test the shear strength of this glue joint. A load of 50 kilonewton is applied. So what do we have? We have P equals 50 kilonewton. Compute the average shear stress in each joint. All right, so what do we have? 100 millimeters, 75 millimeters. If the force is applied from up here, so where would be the shear stress? Yes, the shear stress would be in these areas, you know, in these areas, because it is stuck together in these area and in these area. So these two areas, you know, these two areas would have the shear stress from this side and that side. So these two areas would have shear stress, because if the force is applied from above, it is likely gonna break from these two areas, these joints. All right, so what's the area that shear stress is applied? These two are the areas of where the shear stress is applied. So A equals 75 millimeters in 100 millimeters. So A equals 7,500 millimeters square. All right. Now we have a formula. Tau equals P over A. So how much is the P? P is 15 newtons. But if this is if we are putting this force alongside this axis, 15 newtons is going to be split to 2, right? Because 25 newtons is, if the 15 newtons is going to be applied to the whole joint, 25 newtons is going to be on the right side, and 25 newtons is going to be on the left side, right? Kilonewtons, sorry. So 25 kilonewtons, if we want to just convert it to newtons, and 75 if you want to convert it to, no, let's just 75 for making it easier for us. I want to do this. So the answer is 3.33 newtons in millimeters square. Or we can say 3.33 megapascal. Example 9.11. A punching operation is being planned in which a 1/4 inch hole is to be punched in an aluminum plate 1/4 inch thick. For this aluminum alloy, the ultimate shear strength is 27,000 psi. Compute the force P that must be applied to the punch. Assume that the shear stress is uniformly distributed. So just let me tell you guys something. For example, this is a plate, all right, and this is a punch. With the force of P, we want to apply a force to this punch. So this plate is going to be punched, okay? And when this plate is going to be punched, a disc shape like this is going to come out of the machine. All right, we all have seen the staples and punches, okay? So this is a big punch which is gonna punch plates, okay? So let me just read down the example again and then put all these numbers in the equation, and we're gonna solve this problem. Just to tell you guys something, if you wanna see what's the area of shear stress, we have this formula that we can use for punch. A equals pi dt. So d is the diameter of the disc, okay, the diameter of the disc, and t is the thickness of the disc. Okay, let's read the example and see what we have. A punching operation is being planned in which a 1/4 inch diameter hole is to be punched in an aluminum plate 1/4 inch. So the diameter is 1/4 inch. And the thickness of the plate is 1/4 of an inch. For this aluminum alloy, the ultimate shear strength is 27,000 psi. So we have our tau, which is 27,000 psi, and compute the force, which is P, that must be applied to the punch. Assume that the shear stress is uniformly distributed. So we have the A, we have the numbers for A. So A equals pi dt. So the A is 0.589 square. All right, and our formula is tau equals P for A, since we have tau and A, so P equals A tau. So let me just write down here. P equals, which was our A, 0.589 square. And how much was our tau? It was 27,000 psi. So if we just multiply these two numbers, the answer is 15,900 pounds. So it means that we need 15,900 pound force that this punch can pierce this plate. All right, example 9.12. A tractor drawback is connected to an implement as shown in this figure. The tractor pulls the force of 50 kilonewtons and must be transmitted by the shear bolt. This bolt right here. Calculate the shear stress if the bolt diameter is 19 millimeters. All right, so let's see what we have. P equals 50 kilonewtons. But in this connection, there are two planes of shear resistance to this load. So each plane shear is 25 kilonewton. So we're gonna just calculate with 25 kilonewton since there are two shear planes. Two planes which are in shear stress. And we have the diameter of the bolt, which was, how much was that? 19 millimeters. 19 millimeters. So A equals pi r square. A equals pi 9.5 square, and the answer is 284 meters square. Now we have all the things that we need. Tau equals P over A. Tau equals 25. Since it is kilonewtons, we want to convert it to newtons. And 284 millimeters equals 88 newtons per square, or 88 megapascal. This was for part A. Now part B. Part B of the question says calculate the percent increase in shear stress if the bolt diameter is reduced to 16 millimeter. So first we're gonna calculate the shear stress when it is 16 millimeters, and then we're gonna see the increase percentage or decrease percentage compared to this answer. So first, what do we have? Again, P equals, again, 25 kilonewtons. D this time is 16, if I'm not mistaken. Let me check it again. Yes, 16 millimeters. So A equals pi r square. A equals 314. R is half of the D. A square. So the answer is 201 millimeters square. Again, tau equals P on A. Tau equals 25 newtons, convert kilonewtons to newtons, and 201 millimeters square. The answer is gonna be 124 newtons here, newtons to millimeters square, or 124 megapascal. And now we want to see what's the percentage increase. So 124 megapascal minus this number, 88 megapascal over 88 megapascal. So it is 41.41, and if we multiply it by 100, it is 41% increase.